Hello everyone. Today I'm going to present cybersecurity enhancement of network control systems using homomorphic encryption. What will be discussed today is I'm going to go through a brief introduction on what is homomorphic. Going to go through the problem statement a little bit. We're going to discuss the essences of homomorphic encryption. We're going to go through the encryption of the controller. We're going to go through a quick simulation and validation, and then a brief conclusion. So, why is cybersecurity important in a network control system? It's important because it's really critical to our industrial networks and their infrastructures, and it's really critical to the infrastructures that we have for our public works, such as like water, transportation, and our electricity. So, within that system, there's a controller, and the controller is where it could be exposed to the threats from hacking. It could be targeted for malicious attacks. For whatever reason, some malicious user wants to steal any information, it could be done from the controller. And that's because the control system, it consists of signals, which are it holds the stealing recipes, the policy, and the modeling. And then you have your parameters also, which holds the knowledge about the system's design, and its operation. So the authors wanted to go through and probably solve the problem where they want to conceal the signals and the parameters using cryptography-based control law. So as you can see here in this diagram, right now how it stands is the operator will send a command that's encrypted, and then it's decrypted when it gets to the controller. The controller sends its control input, um, and then that's encrypted and then decrypted at the plant. The plant processes the message, and then it sends its output message, which is encrypted, then decrypted at the controller again. And as you can see, that's a pretty lengthy process, and it can cause some issues because what it does is there's a lot of like each step has to hold a private key to do the encryption and the decryption. So the goal of that is to avoid that. So proposing is to design a system where the operator will send a command that's encrypted. It'll move to the controller, and then the control input sends its message, and that's decrypted. The plant processes the message, and then it sends its message back through the output, and that's encrypted back to the controller. And as you can see, like that's a much simpler and smoother process as opposed to having all those public keys. So what it's going to do is it's going to calculate that encrypted control directly from the encrypted feedback signal, and then reference that while using the encrypted parameters. And what the authors came up with is they could probably use homomorphic encryption to achieve that goal. So as you can see before, the original concept is going to use cryptography-based protection on the transmission signals to provide security from any kind of malicious activity to these controllers. And so before, like I was saying before, the system is required to manage a bunch of private keys, and there lies the potential for any malicious user to perform a hack on the control device, on the decryption device, and then that's going to give them any unauthorized access to the system, and then be able to take whatever information that they need, and that's what we want to avoid. So, but first, before we get into that, I wanted to go through really quickly on what is homomorphic encryption. So it's really simple. It's just a method that performs calculations on encrypted information before it's decrypted, and it allows some calculation on ciphertext, and it'll generate an encrypted solution, and then in turn that'll be decrypted. So what happens is the client sends a message that's encrypted, and then it gets to the server. The server like decrypts it, processes the message, sends its output back to the client, which is decrypted. So It's a really simple process and really easy process, and it should provide some type of solution. So, through for the analysis, the authors wanted to perform their analysis on a linear controller, which consisted of the parameter matrix, the control input, and the plant output. And what they're going to do is they're going to perform that calculation of the public key and the private keys, and they're going to do that within the matrix. And the end solution that we want to achieve is getting phi times xi k, which will equal a function of phi xi k. And to do that, we're going to use some giving encryption schemes to satisfy epsilon. And the encryption schemes that we're going to use throughout the paper is we're going to use RSA, which is really popular today in cryptography, and they're also going to do the analysis on iGamma, which is a little bit more secure than RSA, but that's because it performs a little bit different calculation than RSA would. And so to do that, our end result, we want for our parameters to be a function of epsilon, which is the encrypted phi and an encrypted xi. And then that's going to send a signal. It's going to send this message, encrypted message, to the plant. And then that's decrypted at the plant. The plant will process the ciphertext. And then that'll be encrypted when it sends its output, and then back through the feedback signals, and then back to the parameters. So now we can move into the essences of homomorphic encryption. And what this is, we're going to go through the basic public key encryption scheme first, which really just consists of three algorithms: the key generation, the encryption, and the decryption. And the public key encryption system, it's defined as epsilon equals the key generation, the encryption, and the decryption. And so the generation is done on the private key, and that's going to equal your KP, KS, and that's going to determine the message space move. So once that's determined, we could do our encryption, and on that, the public key for the plain text of the message within move. And we can compute that ciphertext C, which is the encryption KPM is going to be equal to C. And then we could do our decryption of the private key KS for both KP and KS. And that ciphertext C is going to be within C, and then we're going to compute the plaintext of M prime. So the decryption is KSC, and it's going to equal to M prime. So then we can move into the first definition of the homomorphic encryption. So the definition reads that the condition is fulfilled for um, the scheme of being epsilon equals the key generation, encryption, and decryption. So it'll only be homomorphic once these three conditions are filled. So the set mu together with the operation dot product and the set C together with the operation times is going to form a group respectively. And then any plain text in M in mu is mapped into C. And so that's our encryption KPM within C for all of M within mu. And then the third condition that needs to be fulfilled is that for any plain text in M1 and M2 within mu, the corresponding ciphertexts are written as C1. The encryption KP M1 is within C, and C2 equals the encryption KP M2 within C. And then that's how we get our final equation where the encrypted KP M1 dot product M2 equals C1 times C2. Okay, so now we can move into our first encryption scheme, which is RSA encryption, which is defined as epsilon R equals the key generation, your encryption, and your decryption. And so your key generation consists of we generate the public key KP, which is equal to NE. And then we have our private key, KS, which is equal to D. And then we have a k-bit binary, which is N equals P times Q. And for the P times Q, we're going to use two different prime integers. And then we also have E, which is a positive integer coprime to Euler's phi function, phi n, and it's less than phi n. And D is a modular uh, multiplicative inverse of the integer E modulo phi n. So then we can come up with E times D mod phi n, which is going to be equal to 1. And that's what's going to hold our message, our plain text message, where mood is equal to Zn, which the Zn is all non-negative integers. And then so we have our encryption. So we're going to encrypt the plain text where mu exists on Zn, and we're going to be using the public key Kp, which is equal to Ne. And in order to compute that ciphertext C, we need to do mod n, So it'll be m to the e mod n, which will equal C. Sorry. So then we can do our decryption as well. So the decryption is going to be using the private key and the public key in order to compute the plain text for m prime. So we're going to get C to the D mod n, and then that's going to equal our m prime. So this encryption is what allows the homomorphic computation of the multiplication on a ciphertext. And it's with two plain texts for M1 and M2, which exist in Zn. And so that's what we're going to get. So our C1 is going to be equal to our encryption KP M1, which is going to be equal to M to the E1 mod N. And for C2, we're going to get ME2, which is mod N times mod N. And so once the ciphertext of M1 and M2 multiplication, we're going to get our final result, which we can simplify to our encryption being C1 times C2 mod N. Now we can move into the next encryption scheme, which is our iGamma encryption scheme, which is a little bit more complex. So that also is defined as epsilon equaling the key generation, our encryption, and decryption. And so to do the key generation, we generate it on a public key, and that's going to be KP equals capital G, Q, lowercase g, and H. And the private key is just going to be KS equaling S. And then we're also going to have a Q k-bit binary for this one on a prime integer uppercase G, which is in a subset of CP. And that's a cyclic group of the order Q modulo prime P, which will satisfy P minus 1 mod Q equaling 0. And lowercase g will exist in uppercase G, and that's a generator of G. And so S is a randomly chosen element from Z, so that H equals G to the S mod P, and the message space is going to be mu equals uppercase G. So with the encryption, we're going to be encrypting plain text where M exists in uppercase G, and we're going to be using the public key. And so it's going to be in the encryption KPM. It's going to equal G to the R mod P and M times HR mod P. And ultimately, it's just going to equal C2, and then that's just going to be our C. And then R is randomly and it's chosen from Z. And then we can do our decryption on the ciphertext, which is going to use the private key, KS equaling S, and the public key as well. So when we do our decryption of KS and C, it's going to equal C2 times C to the S 1 inverse times mod P, which is going to give us our M prime. And then, so what the iGamma encryption does is it allows our homomorphic computation as well, And you can see it's a little bit more different than the RSA, where our C1 now is going to be our encryption KP M1, which is going to equal G to the R1 mod P M1 times H to the R1 mod P. And similar for C2, it's just going to be G to the R2 mod P M2 times H to the R2 mod P. And what happens is in the ciphertext, we could do our multiplication of M1 and M2 with that random variable R. And where we get R from, R is going to equal R1 plus R2. So we could do our encryption of KP M1 M2, which is ultimately going to equal C1 um, times E C2 mod P, where that times E is just a notation that will denote an element-wise product of C modulo P, which means that in the operation dot product over the set M, it's a multiplication, and the operation times over the set C is a Hadamard product. So one thing I want to note is that the IGAML encryption is considered non-deterministic because the two ciphertexts are computed by M1 equaling M2. And it's non-deterministic because they're not always going to be the same because of the random value R that we're going to compute within the encryption algorithm. So that's what makes it a little bit different from RSA, because RSA is considered deterministic because it doesn't have that random value. It's always going to be the same value. So now we can move into the encryption of the controller. So the idea is the authors came up with the idea that they want to divide the linear into two functions, and that will allow the application of homomorphism. So ultimately what we want to get is we want to get our two functions to equal the function phi psi t, which will equal phi times psi t. Okay, so now we can move into our second definition within the encryption of the controller. So what it states is that we're going to assume that we're given a linear controller F for a network control system, and it's going to have the controller's input V and the output U, and they'll be encrypted by one of the two encryption schemes that we went through just a moment ago. And that scheme is going to also be epsilon is going to equal the key generation, the encryption, and the decryption. And if we can come up with the map with a function of epsilon, then we can come up with the equation that the function is going to be our encryption KP phi prime, encryption KP xi prime, and then that's going to equal our encryption KP f prime, phi, and xi. Now we can move into the realization of the encrypted controller. And within the study, we use homomorphism to realize the encrypted controller. And the homomorphism that we performed on RSA and the IGAML encryptions, that is held for the multiplication. And while the operation of the controller is going to consist of the multiplication and the addition, the operation F will be considered to be a composition product of addition F plus and multiplication Fx. And that's how we get the first equation there, where F is equal to F plus composition product Fx. And where that multiplication is defined in the controller, Fx is going to be our phi xi, which it's going to realize to be our psi. And then from the linear combination of the matrix phi and that vector xi, so phi times xi is going to equal the summation of phi times xi. And you can see at the diagram at the bottom that f of x is now our controller. That's what we're going to do the multiplication at. for F epsilon, encryption phi, and encryption xi. And then we're going to send that signals with the encryption that we did using psi. And then we're going to send that to the plant, and then the plant's going to process the message, do its encryption, and it's going to send its feedback through the feedback cipher using the encryption xi back to the parameters. So, so now we can move into a simulation that the authors went through, and you can see in the second diagram, in the second figure, where they did a simulation result for the time responses on the output Y, and then they did it on the control input U, and then you can see here that there was some quantization errors in the control input response, and the output that was being monitored inside the control device. That one's a little bit scrambled in comparison with the output response, and you can see for the just want to note that the RSA encryption that was done here is deterministic, so it has a steady state. And then at the bottom, you can see that there was a lot of activity throughout the process of the encryption being sent uh, using the iGamma. Actually, that is from the iGamma encryption that was used, and you can see it's a lot of activity throughout the whole process, from when it's encrypted going to the plant, and then the plant sending its output encrypted back to the controller. So what we can realize here is that the authors concluded that with this type of activity, that the encrypted controller that was proposed early in the paper, um, it actually does conceal the parameters and the signals that were processed within the control device. And they also did some validation. So here you can see that both cases of RSA and iGamma identified models were different from the true dynamics. And the author said with this type of validation that we can state that the proposed concept of the control encryption can be effective, and it could be useful for enhancing cybersecurity. We have a chance to go through the problem statement. We discussed the controller and how it was encrypted. They did a simulation and a validation for us. And for future work, they're going to try to do some testing with actually trying to perform some type of malicious activity while doing the encryption using the homomorphic encryption. Thank you.